Hi, I'm Anthony from Berkeley and MIT. Today I'll be talking about two papers regarding efficient unitary designs from two different constructions. These are based on joint work on these two papers with these great collaborators. And let me give a hint that this paper actually will not only be about these unitary designs, but actually also give us a new way to understand and analyze random matrices. So really, the central theme of this talk is about random matrix, random matrix theory, and they really appear in very, very different contexts. Not just in quantum computation, in classical computation, physics, in mathematics. Quite often, you encounter, whether that's a hard random unitary, a Gaussian matrix, or a random permutation. And so it's quite often that in the first scenario where you can just, when you encounter some problem, you would just set your favorite matrix to be random. That's usually not quite exactly a case, but you can do that as a toy model. And then you can use this as a starting point of doing more complex calculations. And it has been pretty successful in modeling, I guess, random graphs, expanders, optimization problem, just consider the problem to be random. And then, so once you define this problem using random matrices, then you can use tools from random matrix theory, free probability. And quite often, still these problems are not completely that easy. You still have to do a bit of work, maybe evaluate some trace of matrix to very high moments to understand its spectral properties, or you might do some Weingarten calculus. That's quite often in quantum computation. And nevertheless, these random matrices are just pretty useful and nice and often give us sort of interesting applications. So this kind of motivates the second scenario where now we know that random matrices are great. We want to find an algorithmic way to emulate them. And by something that's more pseudo-random, but nevertheless, that's more or less the same thing. So it has been very well understood in the classical setting in the sense of these k-wise independent permutations. And really they're analog in the unitary, so in the quantum world, there's unitary K designs. So this K is just an amount of like how many copies you're allowed to query. So this is all information theoretic. So recently people in the quantum community have been thinking about these computational versions of pseudorandomness. So using computation complexity or computational assumptions to argue that you can create random matrices very efficient. However, so through the end of the talk, we'll see that that are the tools we developed to study in the scenario 2 actually ends up telling us about sort of more general application, more general case when you just want to do some random matrix calculation. Right, so we just directly to what our main results are. So the first result considers how you convert efficiently from Gaussians to unitaries. Right, so recall these G's are the GUE, the Gaussian unitary ensemble. These are random Hermitian matrices. And then the claim is that if you take product of two of the exponentials, which is a unitary matrix, then if you choose angle correctly, then this guy is indistinguishable from Har. If your quantum computer can use only sub-exponential many quantum queries. Okay. Right, so kind of surprisingly, just two Gaussians, even one of them looks very different from a random unitary. The spectrum, the Gaussian spectrum is like a semicircle. However, when you just take part of two, it actually just immediately becomes Har random, in the sense of quantum, in the sense of how it looks like to quantum computers. So you might ask, what's the difference between Gaussians and unitary? They both are pretty complicated. However, so with this results in a blue box, we can actually give a different way, a very, very different way of constructing unitary by further approximating the Gaussians. Okay? And in the end, so going through some algorithmic implementations, we can implement these Gaussians using a central limit theorem style arguments by just summing a bunch of random in simpler matrices. And that ends up giving us like n squared k squared complexity. So kind of conceptually, this is interesting because most existing works study spectral gaps. So it's for random unitary circuits. There are lots of machinery that you can use there, but still, it's kind of have been a very long journey, line of work, to push the spectral gap estimates in those analyses. Okay? We and these estimates actually have been very recently improved in 2024. But I just want to say that the argument give here is completely different, and it's based on random matrix behavior. Okay, so the second construction push this further and give better performances by considering another way of approximating unitaries. Okay, so here, what plays a key role is random permutation. So what we do is to take product of independent sparse matrices, right? And what is A's? They are Hermitian matrices made of sum over independent random permutation with complex signs. Okay. Well, and then if you just take an independent product of them with a suitable choice of angle, then this also gives you approximate unitary design at very, very high moments, exponential in n. Okay. And here, so for some technical reason, we can't get the proof works for adaptive queries. Just don't know how to do it. So currently the proof only works for non-adaptive queries. But recently there has been already also be other developments that leads to adaptive pseudo-randomness. So really the blue blocks is what we are able to prove. And then with this, and you can combine with other existing thing that to obtain pseudo-random permutations. So for example, we can really just replace this permutation by k-wise independent permutation, which has been studied a lot in the classical literature. And that would give you also efficient unitary K design. And so this really is inherent from there. It's really not the main contribution of this work. And then there have been a few works that you can, if you want to look it up. So one of them is the very early work of Kasabov, which is like a very powerful result, studying the expander property. I'm giving some explicit generator that have as expander for a symmetry group. And that construction was recently explicitly made, written down as efficient circuit in the recent work. There's also another one in I think also by Kezlov and his collaborators using only finite field arithmetics. And of course, if you like to assume pseudo-random assumptions, like this tolerance of pure one-way function or existence of pseudo-random permutations, then you can also do that, and you give you like also a pseudo-random parallels occur pseudo-random unitary. And so there's also been recent results that improve on this. Right, so these are some recent results in pseudo-randomness and unitary designs, and there has been also lots of improvement already. But for those of you who might be outside of this this business, you might ask, why at all are these relevant to me? Yeah. And so I'll use the remaining of time to tell you a bit about how this actually can be useful as a general principle outside of quantum computation and this T-design business. So let's consider a very general setting where you want to compute some random matrix expression. So in this case, you just take some trace of e to the IGT, where G is like a Gaussian Hermitian matrix. And you want to compute this very accurately, in terms of the dependence on both T and N. So one thing you could kind of do is to reorganize this expansion systematically in orders of 1 over n. So these very often show up in Weingarten calculus, also show up in Gaussian moments. It actually also appears in random permutations and many other random matrix ensembles. So you can do this, but it's often not so easy to compute all these in all the high order terms. So often what's the easier piece is the leading order piece, in this case. This really would be the semicircle for your transform. So, you can look at this up in Wikipedia. However, in order to control all these high order terms, often is a painful combinatorial calculation involved with lots of cancellations. And you have to be very, very careful. And so the one thing that we realize is the following phenomenon. Random matrices actually can be systematically controlled by their leading order asymptotics by the polynomial method. But somehow we found a way to quantitatively exchange limits. In other words, in our calculation, we actually avoid a lot of this painful combinatorics and really argue through the much simpler asymptotic limits. How does this work? So one of the key idea is actually a very, very simple basic inequality by Markovs. So they tell us that a bounded low degree polynomial must have a small derivative. Okay, so if the degree is p, then the derivative on the bounded interval is only 2p squared times the magnitude of the function. So pictorially, it says that if your function is so restricted on this on this 1 by 1 box, and it couldn't oscillate too badly. It couldn't jump in a very small interval. And this this might look very innocent and not so interesting to you. However, it has been a central tool used in a very magical fashion in quantum complexity. And then when this is used, people call it it's polynomial method. So there, the spirit is to reduce something that doesn't look like a polynomial to a polynomial, and often you have to construct very carefully what the polynomial is. But once you do that, then you get this very powerful inequality that gives you the results you want. So in particular, this has been a way to prove a search lower bound for I think forward search, and also the collision bound. That's worked out like 20 years ago. And there, so the point is to argue that there's two cases you want to distinguish, and then you want to somehow construct a polynomial that interpolate between them, and then say that these two cases couldn't possibly change so much. Right. So here, the key insight for random matrix is that random matrix quantity are often low degree in the variable 1/n, where n is a dimension. Right, so what you do is on the x, on the horizontal axis, you just plot all these 1/n points, and you realize when n gets bigger and bigger, it gets very, very close to the origin, 0. Where there it really just corresponds to f of 0, which is n equals to infinite limit. And by the Markov inequality, as long as this function is low degree, whatever function it is, you always have this bound that controls how far it is from the syntactic f equal to 0 limit. You get this very, very simple and actually very just powerful bound on the right-hand side that depends only on the degree, so it's p squared, and also the supremum of the function. And it turns out, so the right-hand side really just have the right form that's very relevant in a random matrix context. So here's how it's going to work. So recall this exponential IGT, the trace of that recalls that quantity. And then we can write down whatever 1/n expansion we have. And here the claim is that we don't care about what these coefficients are. All we need to know is that it's a low degree in 1/n. And then by Markov inequality, this whole thing can be bounded by just p squared times the supreme. Right, and let's just go through the checklist. this function is bounded across dimension because it's like trace e to the IGT. And then but this function, well, it's actually not low degree, but it's very well approximate low degree. And here I think P would be roughly T log T. And there's also this term that you have to truncate them is in dot dot dot. That I think a little sloppy here, but you can do that. And also, so very nicely, it has a large n limit, right? So here, really just coming from the Fourier transform of the semicircular wall. And with all these conditions in place, you really don't need to do anything with the high order term. You just need to truncate them, say they're low degree, you can throw them away, and that's it. And you can just really safely trust the leading order asymptotics, which is the semicircle. Right, so with this principle, we apply this in our main results. So one of the key quantities is to study moments of the matrix we created. And there, well, very nicely, the asymptotic limits is basically none already. You can do it with a quick calculation if you want. And then, so the low degreeness is naturally given to us by Weingarten or Gaussian moments. In our paper, we actually do a slightly more general thing to study just unitary invariant matrices. And there you actually need a little more arguments. In the second case about random permutations, the case becomes a little more complicated because the symmetry class is kind of weaker. I have to do more work. And here we have to consider this distinguishing probability for any possible input and output. So the way the calculation go is to try to think about the larger limit fixing k. You kind of try to swap the limit, just take n to be infinity first, and there permutations become collisionless, and it becomes much easier to reason about. And you can see that these two does agree in that limit. And then for this Markov trick to work, we do need to say that this quantity will be a low degree polynomial. And that's actually pretty technical. We have to construct an orthonormal basis for the EREPs of the partition algebra. So it's like some commutant of this tensor permutation symmetry. We need to show that this guy has also a large n, 1 over n expansion that has a low degree. Right, so now you might ask, okay, you use these tools in these two design context. Can you, does it actually work outside of these models? And the answer is actually yes. So I'll use a very limited time to give a bonus result in a related paper that we're able to apply it to spectral gaps. Okay. So as a very classic questions, people like to think about random regular graph and ask, okay, what is the second eigenvalue? This is just a very, very natural question. And even though this looks pretty simple to state, the proof is actually very, very technical, and precisely because there are lots of cancellations to handle. And there has been recent improvement, but that's still, still you have to capture these cancellation in a very efficient way, and that's still been pretty hard. And so the difficulty in spectral gaps is really not limited to this case. In general, whenever you want to control spectrum of big matrices, some people call this strong convergence, different community. This really requires very problem-specific, intricate techniques. And however, so with this Markov inequality as an input, we get a very soft, proof of this result and much fewer pages. We're also solving other new instances. Yeah. So this cancellation is precisely what Markov inequality is able to capture. In these proof, we don't really deal with all these higher order terms. They're just being systematically bounded by Markov inequality. Okay. And recently, this has also been used in studying sort of the unitary version of these when there's lots of copies, things called tensor product expander. But they actually prove something more general than that. Okay. So that's all I want to share with you. I will just end here with sort of the spirit of this method. And thank you.